Hello everyone, this is Wireless Future. I'm Erik Larsson and I'm here as always with my colleague Emil Björnsson. Hello Emil, how are you today?
I am good. I'm calling in from my home for the first time in this podcast now during the COVID-19 epidemic.
In the midst of the pandemic.
Yeah.
Great to have you, Emil. The topic for today's discussion is going to be millimeter wave communications. And I have been trying to understand where we stand with millimeter wave technology. And I specifically have been rather confused about the terminology itself. So which bands is it really that we call millimeter wave?
So I think that what people are particularly calling millimeter wave in general is from like 30 gigahertz up to 300 gigahertz. So that is when we are sending frequencies that have a wavelength that is from 1 centimeter down to 1 millimeter. So you can essentially measure them from 10 millimeters down to 1 millimeter. But then, as you were saying, there's also confusion because typically what we say that we're using today is from 28 gigahertz, slightly below, up to maybe 60, 70, 75 gigahertz.
Right. So what carrier frequency do we really need to reach? I mean, for the wavelength to be a millimeter long? That would be 300 gigahertz, is that correct?
Yeah, that's 300 gigahertz. And that is sort of the end of the radio spectrum.
Yeah, right, it is, right? So what we really call millimeter wave is rather centimeter wave then. I mean, 30 gigahertz is a centimeter, right?
Yeah, so I think the idea is that you can measure this in millimeters, so from 10 and downwards.
Right, but below 30 gigahertz, do we still speak about millimeter waves? Or where is really the transition point between millimeter waves and lower frequency bands?
Yes, so when people are talking about 5G now, there's essentially two frequency ranges. Frequency range 1, or FR1, which is the conventional one, the low bands below 1 gigahertz, and then 1 to 6 gigahertz. And then there is sort of a jump up to the new frequency range FR2, which is from like 28 gigahertz and then up to probably will reach 75 or something like that during 6.
Right, so either below 6 or above 28. Is that what you're saying?
Yeah.
Yeah, so there's nothing in between then that would be like suitable for wireless comms, or
so
why is
there are definitely some frequency ranges there as well, but it seems like so far there is no access to them. But I've heard people talking about that maybe around 10-15 gigahertz there could be some bands to be utilized in the future as well.
Yeah, it seems to be a lot of spectrum there in principle, right? So what are all those bands used for? Do we know that? I mean, they go between the 6 gigahertz and the 30 or 28 gigahertz?
Oh, there is all kinds of application, and these millimeter wave bands have been used for a long time for, say, satellites are using them to communicate, and in the wireless networks we have been using these fixed backhaul links. When base stations are talking to each other, you might have seen these big round antennas that are pointing not down to the earth but perpendicularly to the earth, and that is sort of aiming at another base station. So those ones are sometimes using millimeter wave frequencies as well. But then there are, I guess, positioning and military applications. All kinds of applications could be in these ranges.
Right, occupy all the spectrum, yeah. So now all this talking about 5G. I mean, is 5G the same as millimeter waves, or does 5G imply millimeter waves in any way?
No, I think the new thing is that you can use millimeter wave in this standard as well. But then unfortunately there's been sort of a impression that 5G is only about millimeter wave. And that is a kind of myth that is propagated still now when like the iPhone is showing up and using 5G, and a lot of other in Sweden, for example, a lot of operators now that are turning on 5G in this part of the year, and then you can hear media talking about that, real 5G isn't there because they're not using millimeter wave, because that's sort of be the issue here, that the only new thing is that now we can use millimeter wave in addition to the conventional frequencies.
Right, so 5G is both lower frequencies and millimeter wave.
Yeah, so they essentially divide into this low band below 1 gigahertz, the mid band between 1 and 6, and the high bands, which are millimeter waves. And I think most of the deployments so far have been in the mid bands, and then in the low bands are also a few base stations that are sort of using both 4G and 5G together.
Okay, so all the deployments of 5G, most of the deployments are in the mid-band between 1 and 6 gigahertz. They were normally referred to as lower frequencies. And so millimeter wave is something that's more like coming for the future then?
In most countries, it is like that. Then there are some exceptions. For example, in the US, there is the operator Verizon that have invested a lot in using millimeter wave already from the beginning in 5G. But otherwise, I think sort of if you read the marketing material from Ericsson and Nokia and Huawei and so, what they are recommending is essentially that you should first deploy 5G in the midband, like 3.5 gigahertz, and then you should take your low band spectrum and share it between 4G and 5G, and that's the next step. You might add a millimeter wave to your network, and then eventually take everything from 4G and turn it into 5G.
Yeah, right, I see. Okay, so I mean, all this millimeter wave technology, or the idea even to use like higher frequencies above, say, 28 gigahertz, because where you said that the millimeter wave spectrum kind of starts, right? I mean, a centimeter of wavelength. Is that a new concept, or how new is it? I mean, for how long has the idea to use millimeter waves for communications been around?
So using it for communication is nothing new. So I think, for example, the satellites, they're using what they call a K-band, which is like 26 to 40 gigahertz. And then there are fixed backhaul links I was mentioning from all the way from 6 up to 80 gigahertz. So there are some different particular frequencies there. So I think the new use case is really the hope that you can use this also for the end users to communicate with their phones. And then the particular challenge is to do it when people are moving around.
Right, so mobility is really the new thing here. That, I mean, it's one thing, I suppose, to have like a dish antenna or something that's fixed and calibrated in its mechanical orientation to point the beam exactly in the right direction, as compared to having a mobile that's moving around and you need to track the channel, right? So is that like the new aspect of millimeter wave technology really that's entering 5G then?
I think that yes, that is one of the new things here. And then, there are a number of different aspects to this. I think the first application will still be in this type of fixed cases where you're using these ones to deliver fixed broadband access to people's homes. And in those cases, also like you put up an antenna at your home's roof, and then you still have a fixed link. But then yes, I think the truly new feature is to try to use this at the street level, put up base station there on utility poles that are using millimeter wave frequencies, and then to communicate with users that are there. That can move around.
So what is really the main benefit? I mean, why would we want to go to these high frequency bands? It seems like complicated because the wavelength shrinks, right? So mobility becomes more challenging, and I've also had the impression that the electronics is much more difficult to develop and produce. Why would we want to explore these bands at all?
So I think essentially the only reason is that there is so much more bandwidth that is available there that haven't been utilized for communication, at least to the end users in the past. I mean, if you're communicating down at 3.5 gigahertz band, you can maybe find 100 megahertz to be utilized for wireless communications. And then if you go up into the millimeter ranges, you can get 10 times that. And why is that useful? Well, when you are communicating, the data rate that you can achieve under good conditions is proportional to the bandwidth that you're utilizing. So the more bandwidth you have, the faster you can transmit.
Right, so you're saying that the data rate that we can transmit is proportional to the bandwidth that we have allocated, right? But see, here's the thing that, we have this from college, this formula, right? Shannon-Hartley formula that states that the capacity of a wireless link is the bandwidth times log of 1 plus the signal to noise ratio. And the signal to noise ratio itself scales as the received power divided by the bandwidth. So when you increase the bandwidth, isn't it that you also decrease the signal-to-noise ratio then? I mean, in other words, if you really want to make use of the increased bandwidth, you have to scale the power proportionally. Is that so?
If you want to make really good use of the bandwidth, yes. You can always add more bandwidth and you will get a slightly better capacity. But if you are not increasing your power while you're adding more bandwidth into the system, you will eventually just reduce your signal-to-noise ratio by, if you have 10 times more bandwidth, you reduce the signal-to-noise ratio by 10 times, and then you get not so much benefit of it. So it's really about either using more power or have a more directive transmission using more antennas, as we talked about in previous episodes, or you just cut down on the range, so you are not trying to serve as large areas anymore. And then you have stronger power.
So power here means received power,
exactly.
I'd say. So this means that, I mean, to maintain a spectral efficiency, because that's what really, I suppose, are concerned about. We want to maintain a given number of bits per second per hertz. Then we would have to make sure that the received power is increased in proportion to the bandwidth. So if we tenfold the bandwidth, then we also have to make sure to tenfold the received power. And you're saying that this could be accomplished through better beamforming with more antennas. It could be accomplished through shortening the range, or be accomplished through increasing the transmitted power itself, or a combination of the three. Is that correct?
Yeah. And then I think that people who are building these type of systems, they are not really hoping that they should be able to exactly provide the same high spectral efficiency as in the lower bands, but to actually say, okay, we can live with a slightly reduction in there if we can use much more bandwidth instead.
Right, I see. So allow some reduction in the spectral efficiency, but still you would have to make sure that the received power doesn't drop too much, right?
Yeah,
I mean,
definitely.
because if you have some power, like a watt or whatever, and you spread it over 10 times as much bandwidth, then the power per frequency unit will be only 10%. So what are the implications in terms of transmission range here? What range are we really talking about for 5G millimeter wave? I mean, I thought for lower frequencies that we could cover like cells of 30, 40, 50 kilometer radius, more or less. I mean, that's what like even early digital systems like GSM do. But for millimeter wave, how long transmission ranges can we cover there?
So that depends on what the actual use case are. When it comes to this fixed wireless access to people's home, I have heard that there are the hopes that you can, in 28 gigahertz band, have a 5 kilometer radius that you can serve. You can serve a lot of homes there with this technology. Then you have very directive antennas. You make sure that you have line of sight conditions, and then you can perhaps deliver 100 megabit per second to all the homes, and many of them more than that. But then you are sort of spending maybe 500 megahertz of bandwidth on that, or at least hundreds of it. So the spectral efficiency is fairly low, but you can still deliver something that is like broadband access.
Right, so the key here is really to have highly directed transmission then with lots of antennas, right? So,
yeah. But then with mobility, it might only be like 50 meters in an outdoor scenario in the city.
Yeah, I see. Okay, but now, I mean, compensating for the, now if we increase the bandwidth, we need more received power. And one way of compensating for that is to add more antennas. So do you make the beam more directive? Is there a limit where this won't work anymore? Or is there like anything else that one would have to consider here?
At start, you would like to have multiple antennas on both the transmitter and the receiver, and that sort of also makes it much more complicated to learn how to point these beams if people are moving around. So that's sort of why millimeter wave have been mainly used for almost fixed scenarios before, or satellites that are moving very slowly. Because you have this directive view, and you need to look around and find the right place to direct your signals.
Right, so really measuring the channel accurately enough in mobility is a main limitation here, you're saying. Yeah, that makes perfect sense.
And one thing to think about as well, when we talked about if you are trying to get away with reducing your power, have a lower SNR, you sort of get hit twice, both when it comes to actually transmitting your data and also when it comes to learning the channels, because if you have worse conditions there, you also get a worse positioning of your beam, and then you get hit from that as well. So it sort of deteriorates quickly under mobility if you have poor SNR.
Right, so just like a squaring effect, that's what you're saying. You get hit twice. First, because the reference signals, the quality of the reference signal scales proportional to the power, and then because the actual transmit power itself reduces. Yeah, that's an important thing. So here's another thought that, when we increase the size of the array, right, we add more and more antennas, then we can make the array gain larger, so we can compensate better and better for say other losses, or we can focus more power at the receiver, so that way increase the effectively received signal to noise ratio. But as we increase more and more antennas, we also increase the spatial resolution, I suppose, so that if we are in a system that is nominally limited by interference, and I would think that a lot of systems are, possibly even at millimeter wave, I don't know, but if we increase the number of antennas, then we would also increase channel orthogonality so that we would reduce an interference. Is there such an effect?
Yeah, there's definitely such an effect. And if you would be comparing one system being down in the mid-band and then the millimeter wave band, then what will happen then as you go up in frequency is that since the wavelength is smaller, the signals are sort of smaller, and it's easier for you to separate signals coming from different directions, and by having then more observations of the signals, if you're comparing the same area, you would squeeze in few antennas in the mid band or many antennas in the high band, and then you're able to separate the signals better. So you might be able to get away with not using as large areas as you would need in the lower bands if you're interference limited, because you're then able to separate them in a better way.
So because of the sheer increase in spatial resolution that we get through adding more and more antennas here. So that has really two benefits, right? I mean, one is that we increase the array gain so we can focus more power exactly to the spot where the receiver is located. And the other is that we improve orthogonality. If we multiplex to multiple users at the time, then we'll also reduce an interference level.
Yeah, so say that we would set up a system like this in a lecture hall, for example, and you have like 100 students gather in the room as we have been used to in the past, then you will probably be interference limited in an environment like that, because the short ranges, a lot of people there, and in those cases millimeter wave will both give you more bandwidth, and you could with a larger number of antennas be able to separate the users much better, even if the size of the arrays are not as large as in the past.
Right. So more bandwidth and more multiplexing to more users at the same time. Wow, that sounds like a real win-win. So what is this good for? I mean, what are the foreseen use cases of millimeter wave technology for 5G?
So I think one of the first things are going to be this fixed wireless access, particularly in countries where broadband access with wires have been fairly expensive. I think in Sweden we have been lucky because it's been subsidized by the government to get fibers to your home. But in countries when that is not the case, then this could be a way to get better wireless access to people in rural areas, because it's so expensive to dig one fiber cable to every home. Then the next thing would then be to have this kind of mobility scenarios over short ranges, both in a lecture hall, and I think that Verizon are putting up in like 60 major cities in the US, and there they are targeting sort of, you put them up on utility poles along the streets, and in the US you are lucky because you have sort of very straight roads, so if you put them to point along the road, then as long as the signal power is high enough, you actually are not having problem that the signal needs to go around corners or anything like that. Then I think a third option is also that we have been utilizing these frequencies for backhauling between base stations in the past. And now we can sort of share these resources between having base station talking to each other and base station talking to users. And in that way, we don't need to have separate systems for these two different things.
Yeah, right. So you're saying basically that, I mean, one use case is to close the digital divide, and particularly on countryside and less developed areas where folks might not have fiber internet access to, instead put up millimeter wave base stations and an access point so that homes could get internet access through millimeter wave technology. And the second would be like more direct access in mobile environments. So you had like a lecture hall or something where folks are moving around with their laptops and the system tracks their location and beamforms adaptively to them. It's an interesting point here with the more straight are the streets, the further the signal can go, right? Because I guess the problem with millimeter wave is that once the wave hits something, then it'll bounce, but it's not going to creep much around the corners. So you won't see like the same diffusion-based kind of coverage that we have in lower bands, but you rather see like spots that are covered and spots that are just all black. Is that a correct understanding?
Yeah, this is sort of a way of picturing it. There is definitely a gradual change between what we're used to, that radio waves can bend partially around corner, and what is also used to when we are using like a flashlight and we light on the corner of a wall and we see that no light is bending around the corner. So there is something in between there that you are getting less bendiness of the signals, and in that way you are having more complication when it comes to actually covering areas. So you will like to, for mobile scenarios, to identify places where there is a lot of people, where the conventional networks cannot provide the capacity that you need.
So, I mean, for the layman, is that like a valid analogy that it's like you're walking in the forest and the sun is shining, then there's diffuse light from everywhere, right? And you can see everything clearly, but then you walk at night when it's all dark and you just have a flashlight and you can only illuminate a precise spot where you're going to put your feet. And so that is like lower frequencies, like illuminated by the sun, versus millimeter waves is like illuminated by the flashlight. Is that a valid way to think about this?
Yeah, I think that's a valid way of thinking about it. And if you have, are you sending one signal beam, then it's like having one flashlight. If you have a base station that is capable of having 4 signal beams, it's like having 4 different flashlights that you can move around and point in different directions at the same time.
Right. So let's talk a little more about physical limitations. So I read somewhere that the path loss is higher at millimeter wave bands. Is that true?
Yes and no, I would say. So it's sort of it's a bit complicated because there are certain things that are definitely are true, and that was how we already touched upon, that you might have worse coverage. But there are also certain things that are often misconceptions. If path loss means everything that we are losing between transmitter and the receiver, or what fraction of the transmitted power that we get to receive, then in most cases you are losing more. But it's not like when the signal propagating through free air that you are being attenuated more. It's exactly the same thing. And sort of the danger is that there is something called a freeze propagation formula, that is telling you how much of the transmitted power that is being received when we are operating at different frequencies and over different ranges when there is nothing in between, just free air. And in that formula, if you assume that the transmitter and the receiver have the same directivity irrespective of the frequency, then you're losing, because the size of the receiver will then shrink with the frequency. But if you're instead assuming that you have a directivity that's increasing, in the sense that you have the same size of transmitter, same size of receiver, irrespective of the frequency, it's the opposite effect. You get more directivity on both sides, and you can then make sure that they are pointing much better. That's essentially what the backhauls are utilizing.
So what you're saying is that, I mean, a correct way of phrasing these claims about path loss is that, well, the path loss per se is no different at millimeter wave bands from any other band, right? However, if we put up an antenna, say a receiving antenna, let's talk about, say, a dipole that we put up here, and there is an impinging field strength from a transmitter somewhere, then the power that this receiving antenna will be able to extract from the field is proportional to the effective area of the antenna, and the effective area of the antenna in turn scales with the wavelength. So is that a correct way of stating this point?
Yeah, that's a correct way of stating it. So when it comes to just the receiver, you would like it to have the same size effective area irrespective of the frequency range in order to make sure that you're capturing the same amount of energy. Think about it like a solar panel.
That's why you need arrays. Yeah, that's why you need either like a parabolic reflector or something, or you need an array of antennas, right? I mean, to get this effective area, because the effective area of an antenna, let's say a dipole, is pretty much proportional to the wavelength. So when you scale the wavelength down, then the effective area scales down, and you need more antennas to cover the same physical area. And to receive the same power as you had nominally.
Yeah, exactly. And then if you're on transmitter side, are also making sure that if that area is the same, irrespective of frequency, you get more directive signals. If it's also scaling down, as you were saying, if you use a dipole that is made for different frequencies, well, in that case, you are getting the same type of effects. It's the same radiation pattern.
Yeah.
So it's really
right. So this is actually So it's actually a fairly simple physical relation, right? So how about all this blocking and penetration loss that we have at millimeter wave? Is that worse than other frequencies?
Yes, so that is sort of where the main difference is appearing. And that is why it's actually generally true to say that you have a worse path loss conditions. It's always problematic to sort of make measurements in real environments and figuring out what is happening. Yeah, I was looking into some different measurements around that to try to get a feeling about what is happening. And it's also like if you're transmitting a signal into a building and then you measure it at the inside, in addition to measuring the propagation losses through the wall, you also are getting sort of multipaths. Signal come from different places, so you measure in one place. At one frequency, you might get a deep fade, and another frequency will have something that is a good condition. But my general impression from reading the literature there is that I would say that the outdoor to indoor losses, if you are going from a 5 to like 30 gigahertz band, is 10 dB larger. So you will sort of only get 1/10 of the power through if you're going up in the frequency.
Right, which means that you would, I mean, to compensate for that, you would need either 10 times higher transmit power, right? Or you need 10 times more antennas to do your beamforming.
Yeah. And then this is also material dependent. So if you have a newly built building that is sort of built as in Sweden to make sure that the heat stays inside in the winter, for example, then those materials might be equally bad for all frequencies, essentially. So I looked also at 3GPP, who was making the standards, and their models for these type of things is that when it comes to a concrete building, there is a huge dependence on the frequency. Higher frequencies, you're losing much more, while if you have like glass or wood material, then the frequency dependence is rather small.
Right, so you're saying that millimeter waves outer to indoor might not be for cold climate countries then, because of the thick walls and all the windows and all that. Yeah. So how about this blocking through humans? I mean, I heard that if you have a millimeter wave transmitter and then you just put your hand in between of the, say there's a line of sight path between this little device and the base station, then you block through, you lose many dB approximately. How much do we lose if you put your hand? Do we know that?
That is also something that one could sort of look into various kind of measurements too. And I mean, the basic effects is something that you see yourself if you just put your hands over your eyes and you are sort of, maybe if you have a very strong light, you can see the difference between if it's dark or light outside, but most things are disappearing. But I found from the New York University, they have made some measurements in the 60 gigahertz range, and in different scenarios there, they saw losses from 15 to 40 decibels. So in some cases you are getting like 1/20th part, and sometimes you're losing almost everything.
Yeah, 40 dB is a lot. It's 10,000 times, right? I mean, it's like going from a transmitter with 100 milliwatt, which is something you could use with a small battery, up to a kilowatt. Kilowatt is like a space heater fan. I mean, that's huge, right? There's no way you could transmit so much power from a base station.
Yeah, then we were always having large path losses in wireless. So if you're close to the base station, you might have minus 60 decibels. If you're far away, you might have minus 110, and that's the 50 decibel range. So maybe if you're close to the base station and you put your hand over the antenna, it might still work. You will just have bad signal quality, but if you are far away, it won't work at all.
Right, that's a good point. So you're saying that the dynamic range of the path loss in a cell or whatever might easily span, 40 dB or more, and then, a 40 dB penetration loss could be acceptable if you're really, really close to the access point. But as soon as you move away a little bit, then it's just going to completely kill the signal.
Yeah.
So let's talk a little bit about technological limitations. So where does technology stand? I mean, for obviously for lower frequencies, wireless transceiver technology is extremely mature, right? And particularly with MIMO arrays, and there are now off-the-shelf products that do massive MIMO with hundreds of antennas. But for millimeter waves, where does technology stand?
So there are commercial products now. So when it comes to sort of mobile terminals, then I think last year, 2019, in the beginning of the year, there were the first products being sold for 5G, and I think over the year, I don't know exactly when, but some of these products were supporting millimeter wave as well. But then it was typically like, if you want to have millimeter wave antennas, you need to pay $100 extra. Now, just some weeks ago, the iPhone 12 was released, the first 5G phone there. And if you buy it in any part of the world except in the US, there is no millimeter wave. But they have millimeter wave antennas in the US version. I don't know exactly how that is affecting the price there, but talking about the blockage of the hand, in that phone, they have antennas at 2 locations, and I think that's sort of a typical way of putting it out to avoid that. So they have on the back side, and they have on the right hand side a small window through the metal, so they hope that you either are blocking the back or the side of it, but not both at the same time.
Right, so you get some kind of diversity effect from having like 2 millimeter wave transceivers on the same, handheld in this case then. Well, that's amazing. So millimeter waves is really a technology that's coming on commercial products now then. Do we know, are these like small antenna arrays, or what are the antenna arrangements on the handsets? Do we know that?
It's small arrays. So Qualcomm have some of their Snapdragon chips for building mobile phones on top of that are supporting these type of things. And I'm not entirely sure what kind of arrays that they have, to what extent you can actually control them. I would guess that they have some kind of ability to change their beams in a simple way.
Right, to adapt, yeah.
Probably not as digital as we are used to talking about in massive MIMO area.
Right, so not fully digital, you're saying. Yeah. So, because there has to be a way of handling mobility, right? It always seemed to me that, blocking obviously is a major issue, but mobility also would be an issue because the wavelength is so short, so that you'd have to relearn the channel much more often than you have at lower frequencies. The millimeter waves, then say 28 gigahertz, then the wavelength is about a centimeter. So you move like a centimeter and your channel is changed completely, and you'd have to relearn all your impulse responses and all that, right, to apply your beamforming. So is that the main limitation, the mobility, or how is this handled in these products? Do we know that?
It is one of the limitations, and I think what is sort of saving the people who are implementing something like this is that we are not targeting very complicated propagation environments. But if you only are having some kind of line of sight like situations, you put up a base station on a utility pole, and then you walk along the street or you drive along the street there. Once you have been able to search around both on your handset and on the base station where to point the beam, then you know that even if the channel is changing, you hopefully are driving in a particular direction. And so for the one who's developing the algorithms, you can try to make use of that. Right.
So basically what you're saying is that you have some prior knowledge about how the channel will change, right? I mean, it's like a little bit like a radar tracking an airplane in the sky. We know that the airplane can't jump from one place in the sky to another. It will fly in some trajectory, so we can actually track it rather than to estimate its location and know from 1 second to the next. Is that how this works?
Yeah, and I mean, satellites is a good example of that. Most of the satellites are moving slowly over the sky, and you know exactly what trajectory you're going to have. And if you put this up on a base station on a utility pole, then it's pointing in a particular direction, and cars are probably driving towards it or away from it. And then you can utilize that for fast moving. And if you're slowly moving, well, maybe it will be much easier if you're just a pedestrian.
Right. So, so here's an idea I'd like to test on you. I've always argued that the lower frequency spectrum is much more valuable than the higher bands and the millimeter waves bands in particular. And the reason I've argued this is that every time you double the wavelength, which means cutting the carrier frequency in half, right? So you creep down in carrier frequency, you increase the wavelength. So every time you double the wavelength, you double the channel coherence time. So you double the number of terminals that you could learn the channel to simultaneously, and therefore you double the number of terminals that you could do spatial multiplexing to, and therefore you also double the number of base station antennas that you would have like reasonably effective use of, and therefore you double like the spectral efficiency in aggregate, because the spectral efficiency in aggregate scales proportionally, as we know, to how many terminals that we can multiplex, assuming that we have enough transmitter antennas at the base station. And some time ago, I looked up like numbers on how much operators pay for spectrum, and then there's a huge difference. I mean, there's an auction that was in 2015 at the 2 gigahertz band, and the cost of a single hertz of spectrum there was almost $700. And then there was last year, or in fact this year, an auction at the 37 to 47, so that's really millimeter wave band, and the cost of a single hertz of spectrum there was only $2. So that felt like a real bargain. I mean, there is a 300 times difference in the value, the market value of an hertz of spectrum at lower bands compared to millimeter wave bands. Do you have any insight into this? I mean, why is the millimeter wave spectrum so cheap? Is it because we can't do this multiplexing, or is it for other reasons? Is it the bargain? I mean, is it time to buy millimeter wave spectrum now?
So I think this might be a good time to buy millimeter wave spectrum for this price. I think the factor that you're describing is definitely something that will at least eventually be very important, that at the lower frequency ranges you are able to handle mobility better, and you it's not like one frequency band or the other but you will like to have all of them, and then you can try to offload some users that are not moving very much to the millimeter wave band where you have coverage, and then you're using other bands in other situations. But then in addition to the argument that you had, there are some other things as well. One is that in the millimeter wave bands there are a lot of spectrum. Say that you have an auction for 1 gigahertz of spectrum, and then you have 4 operators. Well, then they can easily get 250 megahertz each, and they don't need to overbid each other very much.
So you're saying that there's just a surplus. I mean, there's more than enough for anyone who wants to buy a small chunk of megahertz up there. That's why it's so cheap.
Yeah, and then it's also...
Additionally, I mean, yeah, this obviously mobility is an issue, right? I mean, and that argument to its extreme is really what I said, that if you want to do like heavy spatial multiplexing, then the lower frequencies, the easier. But you're saying that there's like a surplus of frequencies that for anyone to buy. Will this remain? Would we speculate? I mean, will it remain forever that there is a surplus of millimeter wave spectrum, or will we at some point in the future hit the transition or a point where that spectrum becomes as crowded as the lower frequencies are today?
It might be that at those frequency ranges, if you have twice the amount of bandwidth or not, it might not make a super big difference, because of these things that if you should make really good use of that additional bandwidth, you need to have twice the power and twice this and that. So I think it might, or it probably will continue like that. But then economical, there's also these other issues that in lower bands, one base station will have a much larger range. So you will have to put up much fewer base stations. So in your budget, it might make good sense to pay a lot for the spectrum so that you don't need to put up so many base stations. While a millimeter wave, you might not want to put so much money into buying spectrum and getting that extra 50 megahertz or 100 megahertz of spectrum, because you know that you will have to spend so much money to put up a lot of base stations.
Right, so there seems like to be overfishing on the lower frequencies, but ample and enough for everyone at the millimeter wave bands, at least so far. Yeah, that's great. All right, so I think it might be time for us to wrap up here.
I think we can say something also about these base stations that are being deployed now when it comes to millimeter wave.
Please do.
I know that what Verizon have been deploying is something that they call the Ericsson street macro. So these are sort of vertical panels, like sectorized antennas. They're like half a meter times 2 decimeters, and then the thickness is also like 12 centimeters or something like that, and then they operate in 28 gigahertz band. What goes into them are some phased arrays, so they are not digital beamforming, but it's not entirely phased either. They sort of have each phased array have like 96 element, and then you could they have half of that, 48 elements, and then you can split it up and form 4 different beams, and sort of each subarray can steer the beam a little bit, and then you can create 2 different beams per polarization, and in that way you can serve up to 4 use at the same time. And I think these ones are also weighs 13 kilo. They are developed in order to have mainly downlink traffic, because that's what they are believing to be utilized, and the output power might be just 100 milliwatt up to half a watt. And I think one reason for that is the short ranges and that you're close to the users, but also that the power efficiency is very bad so far in the power amplifier, so you're burning a lot of energy into heat, and therefore you need active cooling in these machines as well.
So how much do we burn? I mean, because 100 milliwatt output power sounds like almost nothing, right? So even if the efficiency is just like a single percent, say, then the total power consumption would not be more than a small light bulb. So how inefficient are these amplifiers?
I don't have a good number on that, but I would guess it's like 5-10% or something like that.
Yeah, right. So power efficiency here is a major challenge in the design of these units and base stations especially.
Yeah, and it's an interesting sort of trade-off here between what is fundamentally possible in theory and what is practically possible, because in a way more bandwidth should be more energy efficient, because if you want to send with a certain data rate, you need, if you have more bandwidth, you don't need to push as much power into every hertz in order to get that bandwidth. But then it's still not very energy efficient so far, because the hardware is so inefficient.
So the hardware is the culprit here, really. It's not that we need so much more transmit power. At any rate, I suppose you couldn't use that much more transmit power, because at some point, I mean, you don't want to radiate so much power, right? But the culprit is really that the hardware, and especially these power amplifiers, are so inefficient that most of the electrical power you feed into the base station ends up as heat. That has been my understanding.
And this implementation with 4 phased arrays or 2 that can control their different polarizations. This is what is commonly known as a hybrid beamforming method. It's not entirely analog as it would be with just one phased array, but it's not digital because you cannot control all the elements either. So it's something in between, some kind of way of quickly building something that will be enough to send 4 beams, but not as advanced as what we usually call massive MIMO.
Right, so it's quite interesting and quite amazing. I mean, so hybrid beamforming went also pretty fast. It was I think a handful of years ago. I mean, that was like an academic research topic, right? And now it is a mainstream product for 5G millimeter wave. So that's fascinating to see how fast that journey can happen. Great. So I think with that, Emil, do you have anything else you'd like to say here on the millimeter wave topic?
No, I think we have covered all of the important things. If there's something you think that we have not covered, then please send us a comment and we might talk about it in future episodes or respond to it in the question and answer path of YouTube channel, for example.
As always, and thanks a lot, Emil. It's fun to speak with you as always. And to our audience, thanks a lot for listening. Feel free to contact us with questions, and don't forget to like and subscribe us on YouTube. Thank you very much. Bye-bye.
Thank you.